In real analysis, symbols make or change a situation. So in problem number 1 on the true-false exam, we're given this set of information right here. And looking at definition 4.1, the limit of a function, which preserves non-strict inequalities, such as these ones, but it doesn't preserve strict inequalities, like these ones. So our claim right over here, you can see we have a strict inequality. So that means this limit needs to work for all situations, which makes this statement false. This statement's false because it's not going to work for every single situation. So, for example, let's take the function f of x equals to x on the interval 0, 1. That means every value satisfies f of x where it's less than 1. And that's okay, because we could see 0, 1, everything less than 1 is fine. But when we evaluate that limit as x approaches 1 of the function, it's equal to 1. Thus, the limit equals the boundary right there. Instead of being strictly less than it, the correct conclusion would be less than or equal to. If I can get the right color so I can match, just like that. Here we have problem number 2 of the true-false. The statement is true. It is exactly theorem 4.8 in Rudin, and it is an equivalent characterization of continuity. Now, in definition 4.5 of continuity, it's written using the epsilon delta definition. In terms of neighborhood, that says that every sufficient small neighborhood around x naught maps inside the neighborhood around f naught. Symbolically, the definition could be written just like this. Theorem 4.8 expresses the same idea, but from the opposite direction. Instead of starting in the domain and pushing neighborhoods forward, it starts from the neighborhood around f naught and takes the inverse image. That inverse image must contain a neighborhood around x naught. These are equivalent ways of describing continuity, so the statement is true. Definition 4.5, domain to codomain for our function. Theorem 4.8, codomain to domain from our inverse function. Number 3, false. Why? What we have here is a continuous function, and we're saying that if it's a maximum, then it's compact. But this is actually the converse. This is the converse of theorem 4.16, which actually says if it's continuous, then it's compact, and compact, then there's a max and or minimum value within that compact space. Why? If we're continuous and we're a maximum, then we're going to be compact, and no matter what, we can't be proven wrong. So that means we could define a function like f of x equals 0, which is on the real space. It is continuous everywhere, and a maximum everywhere. We can see that on the number line where it extends out. Everywhere is the maximum, but it is not compact. It does not have bounds. It is extending on out from negative infinity to positive infinity, not compact. Therefore, false. Problem 4, set E is in the real space. So theorem 4.15 states that the compactness is equivalent to being closed and bounded. Once we know that the set is compact, then theorem 4 Point 16, the extreme value theorem applies. This tells us that the continuous real value function attains both a maximum, minimum, with our function everywhere in the middle. So for every x in the set, the function is bounded. Problem 5, g is continuous everywhere where x is not 0. That means that there's a discontinuity where x is 0. We're given that f of x is equal to g of x, and so it's telling us that f is now making this function continuous everywhere. What makes this statement false when a function with the first kind of discontinuity can always be made continuous? Well, definition 4.26 tells us that discontinuity of the first kind occurs when one-sided limits exist at one point. While some believe this means the function can always be repaired into a continuous function, this is only true for removable cases, and not for jumps. Let's look at an example. Let's say we have g of x equal to x over x. That means g of x is going to equal -1 at certain places, like when x is bigger than or less than 0. Visually, we have a graph. We have 1 and -1 that cannot equal 1, cannot equal -1. So we have a hole, and we could decide to make a g of x, an f of x equal to 0 to fill that hole equals g of x when x is equal to 0. So now there's a value across the x-axis everywhere, which makes this function appear to be continuous. Except for still right in this section right here, there's this jump. And at that jump, even when we compute the limit on the right and the left-hand side, our limits are not going to come out to the same value, resulting in a limit that does not exist. And for a function to be continuous, our limit must exist. We have a function. And if we take the limit as x goes to infinity, we're saying that it equals 0. Now, how do we know it goes to 0 when we're only given its derivative? Well, by theorem 5.11a, this one tells us that if its derivative, is bigger than or equal to 0, then we know that f, its function, is increasing. And we could see, based on our derivative, I forgot to write that there, as x is approaching infinity, so as x gets bigger and bigger and bigger, our derivative is also increasing and is positive. So it is getting bigger and bigger and bigger. So infinity. That means our function, f of x, which we don't know what it looks like. It's going to look something like our derivative, but we don't know what it looks like, but we do know that because its derivative is positive, then our function is also increasing. And if it's increasing as x is getting bigger and bigger and bigger to infinity, then so is our function. Right now, what we see is the limit with infinity over infinity. This is a result that's called indeterminate. So we don't know much yet about our limit, and so we need to take extra measures. That means we're going to apply theorem 5.13, L'Hopital's rule. L'Hopital's rule states that if two functions approach infinity, just like we have, the limit of their ratio is equivalent to the limit of the ratio of their derivative. That means we could take the derivative of the numerator and take the derivative of the denominator and see what that limit is. So lucky us, we already know what that numerator is because we already have that function, but our denominator, we don't have. That we need to find, and we're going to use the chain rule. The chain rule comes from our theorem 5.5, which if we have a function that we need to take a derivative to, which contains a function in it, that's when we're going to apply the chain rule. So we're going to take the derivative of the exponent part, which is the 2x. We're going to multiply it by the derivative of the e part, which is just itself. And we have some values that end up canceling out, our 2's, our e's, and our e's. And so this leaves us with our limit as x approaches infinity of just 1 over x. So as x gets bigger and bigger and bigger, this is going to 0. So overall, we would say that because of theorem 5.13, L'Hopital's rule, we're able to evaluate this limit and see that we could take the derivative of the numerator and denominator, that it goes to 0. So number 7, the statement is true. By the refinement property in chapter 6, if P star is the refinement of P, then the upper sum cannot increase and the lower sum cannot decrease. This statement right here is an exact consequence of our theorem 6.4. It's where the refined and partition sums converge towards each other. If P star refines P, then adding more partition points makes rectangles more precise. So as the upper sums get smaller and the lower sums get bigger, then from this statement, we can see that the gap between them can't get any larger. All right, this is number 8. The statement is true. By theorem 6.6, a bounded function is Riemann's Zerline integral. If for every epsilon bigger than 0, there exists a partition whose upper and lower sums differ by less than epsilon. So in this case, let's let di represent the difference between the upper and lower sums for the ith partition. The hypothesis tells us that for each successive partition, it cuts the gap in half. Since the gap is being multiplied by 1/2, each step forms a geometric sequence. This sequence converges to 0. So I can choose a partition far enough along the sequence so that the difference between the upper and the lower sums is less than any prescribed epsilon. And since, this tends to 0, we have our gap tending to 0. Therefore, for every there exists a partition such that our given statement from above is less than epsilon. So by theorem 6.6, this proves that the function is Riemann's rule integrable. Okay, so number 9 here we have is a false statement. This includes even and odd values for n right in here. And so anytime we're raising a function to an even power, we start to lose sign information. So for example, let's say we have the function f of x, which equals 1 and negative 1. When x is rational, but negative 1 when it is not. And so this, we already know the function is not Riemann integrable. But let's say we square this and we're going to get a continuous function. Constant continuous function. For this one, we end up with is, but our function is not Riemann integrable. So this makes our entire statement from the beginning for any n inside our natural numbers Riemann integrable for a function. We're on number 10, and this statement is actually false. Not the one on the screen, but theorem 6.20, which is the fundamental theorem of calculus. If you have a function that is Riemann integral, then the function that is integrable is essentially differentiable at a specific point. So for problem 10, what makes the statement false is it states the derivative of big F is equal to little f. This is not guaranteed unless at a particular point where f is continuous. This false statement suggests f is differentiable everywhere. Let's use this function right here. This is a step function. And we can see the graph to the right in green. This function is Riemann integral because it has only one discontinuity. And we can define its function integral by taking the integral f of t dt from -1 to x. So right below it, taking that integral, we are able to define it from 0 when x is less than 0 and x when x is bigger than 0. That's how we got our graph to the right that's showing in blue. Now let's check the derivative back up here. If we're taking the derivative, what happens as we approach 0 from the left side and the right side? These don't agree with each other. These derivatives are different. So this derivative at 0 does not exist. So f is not differentiable everywhere.